So I'd like to introduce Dr. Wayne Higgins. Wayne has utilized his multiple physics and meteorology degrees to further our understanding of all aspects related to climate variability and its linkage to weather patterns over an accomplished and distinguished career as part of several branches within NOAA's climate offices. Wayne has shared his awarded research, discoveries, and knowledge of climate in publications, peer-reviewed journals, and as a speaker, both nationally and internationally. He is currently the director of the Climate Program Office, supporting one of NOAA's climate primary mission goals to understand climate variability and change to enhance society's ability to plan and respond. Wayne will talk to us today about the latest climate trends and their relationship with extreme weather. Let's take a look at this quick introduction video about the Climate Program Office, how they're capturing the human aspects and dimensions of climate change and impacts.
All stations. This is the United States Coast Guard. A powerful storm will begin impacting offshore Monday, the 29th of October.
The evidence is there that in the last 10 to 20 years, there are more extreme events, weather events occurring.
There's no doubt that our vulnerability to these types of extreme weather and climate events is increasing.
Well, weather and climate affect every person's life almost every day. It affects their property, it can disrupt the economy, so it can have a huge impact.
Our forecasters predict and monitor climate routinely by delivering products and services to the nation and the global community for the protection of life and property and for the economic prosperity of the nation.
NOAA can help society improve its resilience to changes in weather and climate in several ways, but primarily by providing the information that people need about what to expect.
Everybody doesn't have to wake up, each day going, I didn't know it was going to be like this, whatever this is. There are ways that you can better understand that this is how your environment is and what you can do to learn to live within that environment and not fight that environment. And we can all be, I think, happier living like that.
Climate is changing, and each of us need to adapt to those changes. Human beings are enormously creative and adaptive species, and with the scientific understanding that we have, I have no doubt that we can, through a combination of adaptation and mitigation, deal with the problems that climate change is going to present to us.
Everybody, I'm Wayne Higgins, Director of NOAA's Climate Program Office, and I'm really honored to be here to speak with you on one of my favorite topics, really, which is the relationships between climate change and trends in weather and climate extremes. I want to emphasize at the outset here that this is not going to be a Climate 101 kind of talk where we talk about how the climate system works. What it's going to be instead is an overview of what we can say about trends in weather and climate extremes and their relationship to our changing climate. And this, of course, I think is a topic that all of us are routinely asked about, especially after extreme events occur, such as the recent cold air outbreak in the eastern two-thirds of the United States or landfalling tropical cyclones like Hurricane Sandy. So the talk will be divided up into four sections, the first two of which are really background information to make sure that we're operating from a common base on our understanding of what climate change is and what global warming is, a particular type of climate change. We'll use that then to launch into a little bit of a deeper dive, looking at trends in weather and climate extremes, and I'll organize the discussion for you around three key issues linked to temperature, precipitation, and coastal vulnerability. I'll finish up with a few key takeaway messages. After my talk, on the order of an hour, Ned Gardner, also of NOAA, is going to step in and provide for you a bit deeper look at some of the climate.gov products and services, and especially opportunities for broadcast meteorologists in using those products and services. So that'll be about a last half hour of the talk this morning. I give this talk in public, and when I do, I usually take great pains to define the distinction between weather and climate, because I find that everybody understands the weather. Whether you're, a layperson or a professional, you look out each day in the backyard, decide what you're going to wear, etc. And of course, climate folks can jump in whenever lay people start to see changes in, for example, extremes in their own backyard. So I want to make sure that we're clear that by weather here, we're defining the particular state of the atmosphere with respect to key variables at a given place and time, such as pressure, temperature, moisture, wind speed, and direction. And for the purposes of this talk, we'll define climate as the expected frequency or normal with respect to those specific states of the atmosphere, but also ocean, land surface, and cryosphere. So in other words, just to simplify here, think of climate as the average of weather over longer periods of time, such as weeks, months, seasons, years, or longer, and that'll suffice. So climate change then is the departure from this expected frequency or average, if you will, or normals, and we'll talk about what climate normals are just to make sure that we're all clear, for a given place and time. And I want to make sure that we contrast this with extreme events such as Superstorm Sandy, for example. Climate change is the long-term shift in the average weather. Why do we worry about it? Well, clearly, temperature increases are going to have significant influences on our activities, where we can live, what food we can grow, our lives and livelihoods. And so to be prepared, there are many questions out there that we have to understand and ask continually to know how much the Earth is warming, for how long it's been warming, how much it might continue to warm in the future, and what the causes might be. And answers to these and other questions obviously provide the basis then for managing risk. And so that is going to be the theme of the talk throughout. Now, later this morning, there will be a talk focused on abrupt climate change, but I do want to mention at this point that abrupt change is one of many types of climate change. And we'll define abrupt change here as shifts that occur relatively quickly, usually over a few decades or less, but that can persist for a long time, decades to millennia. Just a couple of quick examples for you. This is a now famous comparison of one of the glaciers in Glacier National Park. This is Shepherd Glacier. And for those of you like me who are fans of Glacier National Park, we may have to rename the park because it looks like it may be glacierless by around 2030 or so. There's been a major discussion in the research community and, of course, in the much broader public community about the dwindling Arctic sea ice. And so this comparison, I think, really drives home the point that we have major implications, societal, international, for this problem. This happens to be a comparison from '84 and 2012. And in fact, in 2012 September, the sea ice was 49% below the long-term average for that particular month. So we're seeing very serious decline in Arctic sea ice. Water is a really important issue, and I think it's one that doesn't get the attention it deserves. Over 1 billion people rely on glacier melt for fresh water, and this happens to be a look at one of the glaciers above Lima, Peru, which is rapidly disappearing. And we all know that desalinization is a very expensive process, and so I think this is a really important and key issue that we need to make progress on. To give you some sense for the nature of this problem, water is very limited. This sphere here shows all of the water in the oceans, in the seas, in the ice caps, lakes, and rivers, as well as groundwater, atmospheric moisture, and the moisture in you and me, our pets, our plants, all the water. And the bottom line is only a very tiny fraction of that is fresh water. So this is a very serious climate issue. Agriculture. Many of you may be familiar with plant hardiness zones. Plant hardiness zones are shifting. They're shifting northward and rather rapidly. So if we toggle back and forth here, we can actually compare a period from 1971 to 2000 and the period from 1981 to 2010. And by toggling, I think you get a sense of that northward shift. It's on the order of 50 to 100 kilometers, depending upon the particular area of the country. In looking at this particular comparison, bottom line is, if you're in the agricultural community, if you're a gardener, if you are interested in particular tree species, all of these particular elements of our plant hardiness are being affected by this northward shift. Fisheries. 60% of the major fisheries have shifted northward in recent decades, and so I thought I'd show you just one example here. This is a comparison of the red hake distribution along the eastern seaboard. On the left from 1968 to 1980, and the areas in red here show the areas with the, show the areas where we have the largest concentrations in that period, but as you can see, they have shifted much further north, so clearly, you know, if you're a fisherman, that influences your livelihood. Ocean species in general are shifting northward along the coastlines, and in fact, while some species are moving north out of an area, other species are moving in. So global warming then is a particular type of climate change, and the term is misused. So I want to make sure that we have a clear definition that we can operate from again when we then get into the discussion of extremes. So global warming refers to the observation that the atmosphere near the Earth's surface is warming, but there's no implication in the term for the cause or magnitude of the warming. So indeed, what it implies is warming across the entire globe without any element or sense for what might be going on regionally or locally. And so in a moment, I'm going to show you, in fact, there are regional or local portions of the globe where there's actually been a downward trend in temperatures. So let's be clear that global warming refers to the global manifestation of this particular form of climate change. So here's some evidence for what I was saying. The graph on the left shows that global temperatures indeed have been increasing. This is the January to December global mean temperature over both land and ocean. Bottom line is, over the period that's shown there, there's been roughly a 1.5 degree Fahrenheit, or on the order of about 0.8 degrees C, increase in global temperatures. On the other hand, as I was mentioning a moment ago, if you look at the graph on the right, which is the spatial distribution and the changes in average surface temperature, you can see some regional exceptions, such as, for example, in the southeastern United States and over the north-central North Atlantic, where there's actually been a slight downward trend in temperatures. Of course, the recent warmth, we should emphasize, has been greatest over northern portions of North America and over Eurasia, and then again globally we do see this upward trend, as again captured by the graph on the left. So there are many key climate indicators that help us confirm that the Earth is warming, and so what I've done here is I've pulled together a whole suite of them, which are actual records that come from independent platforms, including satellite data, balloons or radiosondes, ships, buoys, etc. And so these independent analyses are shown in these different time series, and then the yellow arrows are meant to indicate whether the trend over the period that's shown is upward or downward. So taken independently and then put together collectively, you can see that air temperatures over the ocean, in the lower atmosphere, in the seas are increasing. Global sea level is increasing, as is ocean heat content. And at the same time, Arctic sea ice, snow cover, and glaciers are all decreasing. So when you put all of these together, they help us confirm from independent analyses that the Earth is indeed warming. Let's not forget the greenhouse effect. Yes, the question.
Just one quick question. Howard Burns, WUSA. How are you able to estimate the ocean surface temperatures going back to 1900, given that satellite era is a lot later than that?
Tide gauges are one of the ways that we do that, and there are proxy records. And a bit later on in the presentation, when we talk about sea level rise, I'm actually going to show you the historical records for those different types of sensor measurements. So I think that might actually answer your question a little more directly.
I guess when I was looking at the temperature change across the globe you had, showing the ocean surface temperatures in the middle of the ocean. So I guess that's what I was asking more. How
If you could just wait till we get a little bit later in the talk, I'll actually show you directly the answer to your question. So let's again talk a little bit about the greenhouse effect. The important point here is that heat absorption by trace gases in the atmosphere, such as carbon dioxide, water vapor, and other trace gases, actually keep the atmosphere much warmer. We should be thankful. On the order of 70 degrees Fahrenheit warmer than it would otherwise be. The concern, of course, is that human activities have increased greenhouse gases over and above what they would otherwise be, and so in that sense have artificially increased Earth's temperature by on the order of 1.4 degrees Fahrenheit greater than they would otherwise be. Are greenhouse gases increasing? Indeed, they are. This is a look from several perspectives at global atmospheric concentrations of CO2. The records on the left are a long-term 650,000 year record. In the center, you see the last 10,000 years, and on the right, since 1950. Indeed, the historical record on the left shows that there have been cyclical fluctuations in atmospheric carbon dioxide. But you can see that since the beginning of the industrial era, CO2 has shot up. And whereas we were averaging somewhere around 250 to maybe 280 parts per million, today we have actually, the last I heard, we hit 400 parts per million for the global atmospheric concentration, with a current rate of increase on the order of about 2 parts per million per year. So I think the takeaway message from this slide is that the concentrations that we're seeing in the atmosphere today far exceed the natural range that we've seen in the historical record going back over 650,000 years. We know where these gases come from. Clearly, it's from the burning of coal, oil, natural gas. It's also from our agricultural practices and land use practices. So we have the control, if you will, to turn things around by basically changing the way that we carry out some of the practices that contribute to these increases in greenhouse gases. Yes?
Before you move on to the next slide, can you explain to the viewers, too, that are watching online, what are some of the natural ways that this is existing, too?
Yep, and in fact, that's the very next slide here. Yep. So that was a great setup. So you know, the natural question for everybody is, how do we know that humans are the primary cause of the warming that we've seen, say, over the past several decades? Because indeed, as was just mentioned, there are both natural and human causes. And some of the natural causes are things like solar cycles. There's an 11-year cycle. Volcanic eruptions. We know that volcanoes will cool the atmosphere for up to several years on some of the stronger cases. And at the same time, we also know that humans can increase greenhouse gas concentrations in the atmosphere via some of the ways that I was mentioning a moment ago. Well, models are what we really have to turn to, and they are increasingly sophisticated in their ways of showing how the different types of natural and human-caused forcings contribute to the warming. And so this comparison here actually shows you the observations, this is for temperature globally, since about 1910 through to about 2000. And that's the black line there. And by the way, I'm always asked, what is that bump around 1940? Well, that turns out to be World War II. And so there are some, I would say, uncertainties in the observed temperature record. So let me be clear about that. Given that, though, what you can do is you can take a climate model and you can try to reproduce the period shown using only the natural forcings, that is, the solar cycles, the volcanic eruptions, and so on. And the blue bar there actually shows the suite of climate model simulations, and it is a suite, so there's a thickness to that bar that sort of captures the uncertainties in the model simulations. And we'll talk more about uncertainties because we need to do that too. But you can see that since 1950 or so, those climate model simulations that use only the natural forcings are unable to reproduce the warming that we've seen over the past several decades. It isn't until we use the climate models with both the natural forcing and the human forcings due to the greenhouse gas increases that we are able to reproduce the observed temperature record. So again, the model evidence, I think, is absolutely key. Yep?
Could you explain how World War II caused an increase in temperatures?
Without a microphone.
Hi, Dave Jones from Storm Center.
Yeah.
So Matt Safino from KGW Portland. Can you explain how, I've never heard that before, how World War II caused an increase in, and I assume these are surface temperatures, or is this ocean and land combined?
It's ocean and land combined, and actually the issue there is I think there were actually a lot more of them, observations, and so what we were actually doing is sampling areas that we don't normally sample, and so I would argue that this record is not homogeneous, the one that I'm showing you here, and that's probably contributing to that bump. But we really should take a closer look at that to explain it more clearly. But I think that's what's going on there. All right, so this naturally then links to the question, sort of the elephant in the room, which is, you know, what can we expect in the future? And future scenarios actually use those climate models, the ones that are able to simulate the past, in order to project future climates by changing key parameters like greenhouse gases to understand how the climate might change in response. But the point I want to leave you with is that you can't credibly project a future climate without being able to simulate past climate. And so that's why I've been emphasizing that we need to see whether or not the model is credible in the past in order to think about whether it's useful in the future. Now, this table, I really like this table because it puts in perspective for me, you know, the current climate model capabilities to simulate past climates and the level of interest that that has for decision making. And so if we look at, on the left, mean annual global surface temperatures, I think it's fair to say that with today's fairly sophisticated coupled climate models, we have a pretty exceptional ability to reproduce the past 50-year record. But most decisions are made at regional to local scales, so the level of interest to a decision maker is really pretty low for that parameter. On the other hand, if we start getting into more regionally specific and higher temporal frequency information, say seasonal forecast, for say surface temperature or precipitation, or their year-to-year variability, for example, as controlled by El Nino and La Nina, as an example, the level of interest to decision makers is getting higher, but of course climate models have only really, I would say, a fair ability to reproduce surface temperature and a pretty poor ability actually to do precipitation. Going to an even higher spatial and temporal resolution, when we're starting to talk about things like extremes, and we're talking about, say, how they might vary, you know, from week to week or over the course of a month in a regional or seasonal kind of specificity. Obviously, the level of interest is very high for decision making, but climate models are pretty poor. One other point I'd like to leave you with before we then launch into the discussion on extremes is that future changes are obviously going to depend on our near-term choices. So what climate modelers frequently do is they use temperature projections to look forward in time using what they call emission scenarios. And I'm actually showing you 3 here from a recent assessment report. in which the climate models are run many times into the future using these emission scenarios. In this case, it's a comparison of maintaining CO2 at current levels, that's the 2000 levels, a lower emission scenario, which is basically a doubling of CO2 by 2100, and a higher scenario, which is quadrupling CO2 by 2100. And then the climate models are run many, many times, and these cones actually indicate the growth of uncertainty as you move forward in time. So based on the growth of those model errors, combined with what your risk tolerance is, you can decide how to employ or not the use of that information. For climate modeling, obviously a key issue is reducing uncertainty. And just to be really kind of like boil it down, uncertainty, of course, is a measure of how well we know something. And if you're a climate modeler, there are many things you can do to try and reduce uncertainties, ranging from trying to improve the dynamics or the physics in the model itself to using multiple climate models in what we call ensembles to try and capture that range of uncertainty. As I was mentioning a moment ago, that's what these cones actually illustrate in this particular set of projections. So reducing uncertainty then is really the key to answering those questions that we want to really address with confidence, such as how much of the warming is due to anthropogenic versus natural causes, and how much warming might take place in the future. Okay, so now we're ready to talk about weather and climate extremes. And one of the things that I always like to emphasize, again, going back to the opening point that, you know, people understand the weather, but climate is conceptual and kind of fuzzy. But it's important to emphasize that this is a continuum we're talking about, and that there are extremes on all time scales. So we're all used to thinking about, you know, tornadoes and snowstorms and hurricanes and heat waves as extremes. But as we move to slightly longer time scales and talk about things like storm track variations or teleconnections from the tropics into the mid-latitudes, or tropical phenomena. One of them that I've got listed here is the Madden-Julian Oscillation, which is a tropical disturbance that modulates, for example, tropical cyclone activity in all of the ocean basins on these time scales that are on the order of 30 to 60 days. These are extremes. As we move to seasonal to interannual timescales, we're talking about phenomena such as El Nino and La Nina, which of course influence the storm tracks and hence influence the numbers and types of extreme events on daily timescales. So important point here is this is a continuum, and this linkage between weather and climate extremes is really pervasive. Why do we care about extremes? Well, obviously they have profound consequences. They affect our lives, our livelihoods, where we can live, what we can grow, and so on. And there's increasingly compelling scientific evidence out there that the nature of extremes is altered by climate variations and change. Again, it's a continuum. So increasingly we have actually an exponential increase in the demand for this kind of information from decision makers who are trying to address or answer societal questions, including those that influence where we can live, our livelihoods, our businesses, and the ecological systems that support us. I think this is a really dramatic diagram. It's from Munich Re Insurance. It shows natural disasters over the period from 1980 to 2012, but they've been broken out by different types. So there are geophysical events, there are the meteorological events, basically storms, which have been separated here from hydrologic events such as floods and landslides. And then climatological events such as heat waves, droughts, forest fires. The main point, though, is that these disasters, possibly with the exception of the geophysical events, are on the rise, and this has translated into record economic impacts in recent years. And you can look at this from the point of view of insured losses, which is exactly the way that it's being scaled here. The numbers of these events are clearly on the rise. We can look at it also from the point of view of billion-dollar disasters. So this looks at the breakout of billion-dollar weather and climate disasters over a similar period, 1980 to 2012. But the interesting thing here is we've broken it out by state and by type of extreme event. So the message is that no state is unaffected by these types of billion-dollar events, but when you break it out by type, such as drought and heat waves or hurricanes and tropical storms, you can begin to see that there are some areas of the country, such as the south central United States and the southeastern United States, where several types of these billion-dollar disasters are common. So let's now talk about three key issues, the first of them being temperature. And let me emphasize that, when we talk about heat is the #1 weather-related killer in this country. In fact, I believe that heat is responsible for more deaths than hurricanes, tornadoes, floods, and droughts combined. And so it is a very, very important issue. In my talk this morning, I'd like to emphasize how changes in trends of maximum and minimum temperature are occurring in the United States, and also what that implies then for changes in things like frost-free days, and also numbers of highs, record highs and record lows. So let's start, first of all, by looking at the observations. This happens to be a comparison of the normals. Remember, normals or longer periods. In this case, these are 30-year normals, which is a world meteorological standard. So what we're looking at is simply the difference between the period 1981 to 2010 and an earlier period, 1971 to 2000. Max temperatures on the left, min temperatures on the right. Bottom line is every state in the lower 48 has shown a shift towards warmer maxima and warmer minima. Again, because these are normals, it's just a fraction of a degree that we're talking about here, but that is very, very significant when you consider that this is averages over 30-year periods. So there's this distinct shift towards warmer normals for both max and min. I mentioned a moment ago that we're also seeing changes in frost-free season length, which is the length or duration and number of days from the last 32-degree day in the spring to the first 32-degree day in the fall. This happens to be a comparison of a recent 20-year period, 91 to 2011, as compared to an earlier period from 01 to 60. And we've actually seen double-digit increases in several areas of the U.S. In the length of the frost-free season. I mentioned a moment ago that we're also seeing increases in the ratios of record daily highs to record daily lows. Indeed, that is shown here in this diagram, which gives you the information by decade. So you can see the Dust Bowl era was kind of an exception. It happened to be an era where there were many more record highs, and so the ratio was about 1.5. But with that exception, you can see that since the 1940s and 50s, we've actually seen an increase, especially in the 2000s, to where we're running at a ratio of about 2 to 1. And as it turns out, when you really get into the details here, this is due in large part to the very small number of record low temperatures. So carrying forward that theme, I thought it would be useful also to look at temperature observations with some attention to the daily low temperatures. And so in fact, this looks at trends in the number of days with unusually warm daily low temperatures over North America. And you'll see in particular over the western sort of half of North America that there is an increase in the number of days per decade, in this case, with unusually warm daily lows. But let me emphasize, this is just one piece of information. If you look at recent assessment reports, you will see that there's also been increases in unusually warm days. There also have been fewer unusually cold days and nights. And again, there have also been increases in the number of heat waves. But the 1930s does still remain the decade with the largest number of those. Again, continuing in this theme about the very warm nights, I wanted to also show you some projections of temperature, again recognizing that the confidence for temperature is relatively higher than it is for other parameters. So here I'm showing, again, the observed temperature record as well as some simulations of that observed record, which are relatively more confident, and then a suite of climate model projections for different emission scenarios. It's not so important that I explain to you the details of those scenarios, but what is important is to notice that all of the scenarios show upward trends and in this particular case, the percentage of very warm nights, which happens to be the top 10% of the temperature distribution in this case. So whether you have low risk tolerance and you need to use a 95% confidence interval, or you have a relatively high risk tolerance, sorry, I said that backwards, and you need to use the 95% confidence interval. Bottom line is we are anticipating from all the climate model projections increases in the percentages of very warm nights, also very warm days, and then decreases in cold days and cold nights. Let's talk about precipitation. Here we're talking about changes in precipitation intensity and frequency of heavy rain events, changes in drought frequency and intensity and duration, changes in snowpack, which influence runoff and are, of course, of key interest to water resource management in this region and much of the West. So I thought I'd start again with the observations, emphasizing the percentage of the U.S. with much above normal one-day heavy precipitation. This happens to be events that exceed 2 inches, and again based on annual information for a fairly long temperature record. And you can, precipitation record, and you can see that, especially since about the 1980 time frame, there has been an upward trend in these precipitation extremes as measured by this particular parameter. If we want to look at it in a more regional context, this happens to be the percent increase in the amount of precipitation falling in these very heavy rain events, which here are the heaviest 1% of all daily events over a record that extends from 58 to 2011. And we're seeing double-digit increases in most areas, and in fact in the upper Midwest and the Northeast, the increases are pretty substantial in terms of the amount of precipitation that's actually falling in these heaviest rain events. Looking at projections, I think, is very, very interesting. This is the changes in seasonal precipitation mid-century, 2041 to 2070, as compared to current, in this case, normals from 71 to 2000. Focusing your attention on the spring and summer, you'll notice that the southwest monsoon, especially in the summer period, is showing up as being weaker in mid-century. And so, of course, if you live in Arizona or New Mexico, where you rely on 50% of the annual precipitation from the southwest monsoon, this is a very serious issue. On the other hand, notice that in the winter in particular, but also in the spring and fall, areas of the north central United States and also the northeastern United States are projected to show increases in seasonal precipitation. I rather like this particular diagram, which shows projections in precipitation across the entire range of precipitation intensities, from the lightest events to the heaviest events, with several emission scenarios. Again, here it doesn't matter, the details of the emission scenarios don't matter as much as the message, which is that the lightest events are projected to decrease slightly, but you can see that the heaviest events are projected to increase substantially, especially for the strongest emission scenarios. Last issue I want to dive into here is coastal vulnerability, and we'll get back to that data issue that came up a few minutes ago. Here we're talking about rising sea levels, and as I'll show you, sea levels have been going up rather steadily and rapidly, but there are regional variations in that, so we'll look at that. And obviously, if sea levels are going up, what folks along the coast care about is total water levels. So in fact, if we have increasing storm intensity, as we were talking about yesterday in Rick Knabb's talk, and we're talking about storm surge, flooding, tides, and so on, that we have to factor in the increasing sea levels as we have this conversation. So it's not just about the next storm in terms of the storm surge and flooding, but it's also the fact that this is riding on sea levels which are going up, and in many areas, particularly the mid-Atlantic, but also portions of the Gulf Coast, we also have land subsidence. So you have the land sinking, the sea levels rising, and on top of that, stronger storms. So let's talk a little bit about sea level rise. Let me just summarize the global statistic, which is that the global sea level has risen about 8 inches since essentially 1880, which is when the proxy records and tide gauge information goes back to. When we focus on the relative sea level change along the U.S. coast, and this happens to be a shorter period from 60 to 2011, you can see that in many areas it's going up. In fact, in portions of the Gulf Coast and Mid-Atlantic, it's going up rapidly. There are regional exceptions, though. Look, for example, along southeastern Alaska coast and along the Aleutians, there are actually downward trends in sea level. Just to remind you, earlier we were talking about some of the causes of sea level rise, and clearly this is related to not only the warming-induced expansion of the oceans, but also the fact that we have melting of many of the world's glaciers and loss of the Greenland and Antarctic ice sheets, which is also contributing to sea level. So this then shows projected sea level rise using information from a series of different types of measurements. There are proxy records that go back to from 1800 through to about 1880, and then the tide gauge data picks up in about that time and comes forward through to the present. We pick up satellite data around the late 1970s, early 1980s. However, what is shown here actually is since about 1993, and you can see that the comparison in the blow up there in the top of the diagram for the period from 1990 to 2012 of the tide gauges and the satellite data, the comparison is pretty good. So I think the data is pretty reliable. And then we have projections that go forward through to 2100. So again, where your risk tolerance is relatively low, you might want to use the very broad and uncertain range of 8 inches to 6.6 feet. But if your risk tolerance is higher, the projections of 1 to 4 feet are pretty widely used. But the bottom line is, irregardless, the sea level inexorably is continuing to rise. What does that mean? So let's talk about Gulf Coast transportation. Yesterday, Rick Knabb was showing you information on storm surge. Well, this is information on sea level. What's shown here are interstates and other highways that lie at or below 4 feet. And so you can see that a significant portion of the Gulf Coast is at risk for increasing sea level, which, based on the climate model projections, 4 feet is well within the risk tolerance range that many decision makers consider acceptable. So this is a serious issue, and in fact we could do the same kind of analysis along the Mid-Atlantic coast and draw similar conclusions. I wanted to also show the New York City and sea level rise issue again. What's shown here are the 1 in 100 year flood zones for New York City, and the FEMA current 1 in 100 year flood zones are the areas in purple, but also shown then are some projections based on a sea level rise of 9 inches in red, a sea level rise of around 27 inches in orange, and a sea level rise of around 53 inches in yellow. And remember that these are values that are near the bottom, I would say, of the ranges in the current model projections. So again, a very serious issue. And I will say, going back to some of the work that's being done in New York to develop adaptation plans and actually begin to implement them, that I think one of the really key issues here is to begin to address the societal impacts associated with this inexorable rise of sea level, combined with the increasing intensity that's anticipated for landfalling tropical cyclones and other types of storms such as nor'easters.
Excuse me, Wayne.
Yeah.
Jim Cantor, Weather Channel. On that graphic, was there any type of projection in terms of population that exists in those zones as well, going through that the years?
I have not seen that, but I can tell you that from other sources that I have seen, somewhere between a 20 and 40% increase in the populations along the coast by 2050, I think it is, compared to where we are today. That number may be a bit low. So the bottom line is population is increasing. Our risk, our vulnerability, I think is the key point, is increasing. And if you combine that with what is happening in the climate, I think we have an increasingly serious problem that we need to address through adaptation planning. I can get the information for you on those projected increases in population in the coastal communities if you're interested in
Yeah,
that.
anything from current to even the next 20 years would be great. I'd like to know how many people live in there.
So the increasing population along the coast combined with the projections that we have for increasing sea level and increases in storminess suggests that we have a very, very serious issue. Emphasizing New York here, of course, but really it is the entire seaboard, eastern seaboard, Gulf Coast. And let me not leave out the West Coast. In some areas, as I showed you, sea level is decreasing, but that doesn't diminish the increases in storminess that are projected in some of the projections I've seen, where we still are going to have winds, waves, tides, and surge issues.
Thank you.
Mm-hmm. Yesterday we were talking a lot in Rick Knabb's presentation about tropical cyclones on shorter time scales. And I do want to emphasize that this is a very difficult problem when you start talking about trends, because we have all kinds of problems with the historical record, for example, pre- and post-satellite era. Prior to the early 80s, late 70s, we didn't see every swirl out over the Atlantic, whereas since then we do, and in fact one could argue that the numbers of tropical cyclones are artificially high because of that fact compared to the earlier record. However, that aside, when you look at intensity, and use various indices. This happens to be a power dissipation index, which is basically related to wind speeds. There is year-to-year and even decade-to-decade variations, as shown on this graph, but overall, since the late 80s, or around 1990, there has been this upward trend in intensity. And when you look at climate model projections, this happens to be a comparison of late in the century as compared to 2001 to 2020. The projections pretty much universally show an increase in the strongest storms, that is the category 4 and 5 hurricanes, and a smaller decrease in the weaker storms, so the tropical storms and the weaker hurricanes. I like this graphic because it summarizes sort of the state of our scientific knowledge with respect to extremes, taking into account whether or not we can observe them and whether or not we understand the physical causes. So think of this as the adequacy for our ability to detect them and to understand the causes of changes. So along the x-axis we actually have detection, with less knowledge being to the left and more knowledge being to the right based on observations. And along the right axis we have understanding causes, again less knowledge, in other words less physical understanding to the left and more physical understanding, down and up. Bottom line is the state of knowledge for the various types of extreme phenomena is widely varying. There may be some debate out there in the weather and climate community about the exact placement of these based on your own personal experience. But more or less, I would argue that, precipitation, heat waves, cold waves, floods, and droughts are sort of at the higher end of the spectrum, whereas our physical understanding and ability to detect thunderstorm winds and ice is sort of at the lower end. So there is a positive correlation here between detection and understanding, and it is widely varying and does depend on the data that we have available and our physical understanding of the processes. So I think this is a very important sort of summary of the state of extremes. And then finally, let me say that again, going back to the point I made earlier that the demand is really exponentiating across space and time scales, I thought it would be useful to kind of look at some of the local, regional, and national products that we currently provide and on the different time scales. And since this is a climate talk, I started with weekly, monthly, seasonal, and went out to decadal. So what you see on the top are some example products. I picked actually Louis Uccellini. There are many, many gaps to fill. And so that NOAA, working collaboratively with other agencies, and then working with the broader community, the private sector, is trying very hard to understand user needs for this information, and then to tailor that information in a way that helps us provide information that can be useful for risk management and decision making. So let me summarize now with a couple of key takeaway messages for you. I hope I've convinced you that climate change is a key issue. I think it's really one of the key issues of our times. There's clearly overwhelming scientific consensus on the facts. The Earth is warming. Human emission of greenhouse gases is the primary reason. There will be adverse consequences. There already are adverse consequences. And humans can and should mitigate and adapt to the problem. Links between weather and climate are pervasive. I always take the climate discussion back to weather-climate linkages. People get the weather. A local manifestation of climate variability and change, climate, is changes in the number and types of weather events, including extremes in your own backyard. So people, when they begin to notice changes, that's when they start asking questions, and that's where I, as a climate scientist, can jump in and try to provide some answers and information that they can use. I've tried to show you rather quickly that there's some observed and projected trends that are well documented. In the U.S. in particular, heavy downpours are increasing in many regions. Heat waves have been most prevalent in the West, droughts also in the Southwest. We have a very severe one that has emerged now in California. Global sea level rise is projected to increase, and I think in particular along the East Coast and the Gulf Coast, we have a very serious issue when you combine that with trends in other types of events such as storm surge associated with tropical cyclones, which are also projected to increase. Again, there is local variability, and so it's very important to understand your local context. Projecting local impacts is difficult. Regional scales of these projections frustrate local decision makers, and I mean that. So we have a long way to go. There's a lot of research that needs to be done. That research needs to be tied through the climate modeling projections to useful information that decision makers can use. And finally, I wanted to emphasize that NOAA, working with partners, is trying to improve development and delivery of useful climate information to support those decisions. We have a long way to go on that, and in fact, I've had some great conversations with folks here at the summit about the need for mechanisms to sustain engagement between public and private sector providers and users of climate information and weather climate information. So let me just emphasize that I think that, at least on the climate side, it's very much in its infancy, but there is, I think, a lot of scope for progress in the near term, working on lessons learned from the weather community. So I look forward to that conversation, and thank you very much for the opportunity to provide you with an update on where I think the science stands with respect to climate change and trends and extremes.
That sounds great, Wayne. Thank you very much. And what we're going to do now, as with all speakers, we're opening it up to questions. And so please raise your hand, and we'll get the microphones distributed in order of your hands raising. Bernadette and then Howard will go. And then after we get finished with the question and answers, what we'll do is introduce Ned Gardner, who will tell us about some resources available through climate.gov. So let's start with Bernadette.
Thank you, Wayne. This is Bernadette Woods-Blackley with Climate Central, and one thing I'd just like to hear you talk a little bit more about. I know they're not exactly the same, but there's so much talk about Arctic sea ice versus Antarctic sea ice right now, so I would like to just hear your words on that.
So I didn't address that issue at all in my talk, and I didn't come prepared to show you sort of the comparison of the decline in Arctic sea ice and the decline or lack of decline in the Antarctic sea ice. But I will say that inexorably, as the climate warms, both in the Arctic and the Antarctic, we are seeing a decrease, a trend. Towards decrease. Now, I know that there's a lot of research out there in its infancy about, what accelerated changes in the Arctic and Antarctic might mean for the globe. And so, for example, there was a recent, very widely broadcast discussion about, okay, if we have declines in Arctic sea ice, what does that imply if we have a warmer Arctic for the potential for more cold air outbreaks in mid-latitudes? Let me just say that, and leave it at that, there's a lot of ongoing research there that's in its infancy, and I think to comment beyond the fact that, our historical observations really don't support, confident answers to the question, and that our modeling community, both from the simulation and projection point of view, is really just getting started on the problem, that it would really be premature for me to make a judgment here. But I am, as the director of the Climate Program Office, very interested in the Arctic and Antarctic problem, and look forward to actually working with the broader research community on the topic.
Well, thank you. That was my second question, was the Arctic amplification, but I think you just answered that too.
Okay.
Thank you.
Yeah, Wayne, Howard Bernstein, WUSA in Washington. We've got increasing populations, and is that one of the main reasons, or let me rephrase that. Has that been considered when you're talking about the increase in the reported and observed extreme weather events? How many of them have been actually missed in the past because we had much more sparsely populated areas in different ways? And how do you normalize for that when you're doing your data and showing that? And to follow that with the billion-dollar weather events, are those being adjusted for inflation versus something like in the 1975 versus 2000, so that at least we're comparing apples to apples?
The second question is the shorter answer, which is yes, they are adjusted for inflation. And I think the particular example I showed you was adjusted to 2000 or something like that. But they are adjusted. Going back to the first question, obviously, first of all, let's dismiss over the ocean. Obviously, pre and post satellite era makes a big difference, right? Especially if you're looking for tropical cyclones. Over land, I think the key message I want to leave you with is that our vulnerability as a society is increasing as more and more people move to the coast. You can look at the demographics and you will see that there is an upward trend along all of the coastal areas, and particularly, I would say the Gulf Coast and in the Southwest. Those trends are upward, but also more and more people, in the Southeast as well. And so if you couple that with the climate model projections for increases in the various types of extreme events, such as the strongest tropical cyclones, as a society, our vulnerability is increasing. And so as a planner, I think it's just becoming increasingly important to develop adaptation plans. So what does that imply, for example, building along the coast? Or if you're designing and siting a power plant, and it's a nuclear power plant, and you need to cool the plant and see, water is getting warmer on the one hand, and you're also anticipating more extreme weather events in the future. What does that mean in terms of designing and siting your plant? So on, there are many societal questions like that, and so I simply want to emphasize that I think going forward we need to, first of all, understand what the most serious issues are. And I would argue that sea level rise coupled with storm surge is one of them. And then tackle, through the development of implementing adaptation plans, begin to tackle these issues by tying the physical and social sides together more decisively. And that's another, by the way, dimension of this problem, is that in the past, our physical scientists haven't worked as well as they should with social scientists to actually get the message, understand the user needs, and then get that back to the developers who are actually trying to, to improve the models to make the climate model projections more confident.
Jennifer Gavina from WPSD in Paducah. I just wanted to make sure that the message that I give my viewers is correct, but you know, especially in the last couple of months, we've been seeing stories go around about going back to the Antarctic and how there's more sea ice. But isn't it true that in the Antarctic, we've got much younger sea ice that is more exposed to melt in the melting season that we see naturally, whereas in the Arctic, we're losing very, very old ice that we can't get back. But we are seeing, I mean, we're seeing ice annually up in the Arctic, but it's much younger ice, which is also exposed to that melting season much easily.
So thank you
Easier.
very much for that clarification. And in fact, even in the Antarctic, the young ice versus the old ice is part of the issue when you look at trends. So you've got the message exactly right, and I think it is important. And I am not an Arctic ice scientist, so I don't really want to delve into the details, on exactly what the state of the art is in the research community on that topic. But the long-term trend overall for the old ice is downward in the Arctic, and I believe also in the Antarctic.
I don't know if Jim, is Jim in here? Yeah. Can you add to the Antarctic? Is it much younger sea ice, whereas in the Arctic we've got much older ice that's being lost?
It's Jim White, University of Colorado. Antarctic sea ice is generally formed every year, so you get large extents of basically one-year ice that melts back all the time. It's just a fundamentally different situation because you have a continent surrounded by ocean in Antarctica, and you have an ocean surrounded by continents in the northern hemisphere. Does that answer your question? Or?
Yeah, because I just wanted to answer that, the article and people putting out there that, climate scientists are getting stuck in their own ice down in Antarctica, and it's a much different story than that.
I really appreciate that clarification. Thanks. Yeah.
Howie Bluestein, University of Oklahoma. I'm curious to find out why the sea level is projected to decrease around Alaska. It just seemed to me that with all the glaciers and snow in British Columbia and Alaska, that the sea level should rise. What's acting to mitigate that?
Howie, I don't know the answer to that question. I'll be upfront. I'm not an expert on the regional variability. I'm just showing you this graphic. So I think what we'd have to do is take this offline and go back to. Oh, you can. Awesome.
Yeah. Howie, it's land rising and subsiding, so it's tectonics. So Alaska's coming up out of the ocean. So Alaska, actually sea level will be dropping even faster in Alaska if sea level wasn't rising against a changing Alaskan coastline.
So Jim, let me ask you a question then. So for the areas where it's rising most rapidly along the mid-Atlantic coast and in portions of the Gulf Coast where we also have land subsidence, could we argue that that's taken into account here as well?
Yeah, this map does take into account a number of things. There's land subsidence, but there's also, as you know, if ocean currents change, if you've got a strong ocean current pushing water up against a coast, that actually keeps sea level high in that area. If those winds change over time, then where the water piles up changes, and that also impacts the projections for sea level rise. And these can be substantial, 6 inches to a foot kind of changes.
Thanks.
I just had one question, maybe both of you guys. Howard Burns, WSA in Washington. You're talking about the sea ice, but in the Antarctic, isn't the ice on the continent? Have I missed that, or is that not increasing? And it would make sense if it's a slightly warmer, we'd have more precipitation events, and that ice on the continent can build up. And is that being taken into account? Because there's been no mention of that.
Yeah, there's a little bit of increase in land ice in East Antarctica, a decrease in West Antarctica. At the moment, I would say it's probably a wash, maybe a little bit of an increase, but it's not huge. And there's an expectation we'll continue to see some ice build up in East Antarctica as that area warms up. It's not enough to counteract everything that Wayne has said here about sea level rise. And all of that's taken into account in the longer term projections, which is why, as Wayne pointed out, you get these fairly big cones of uncertainty.
Yeah, John.
Greg, go ahead. I'm going to take it in a different direction, so if you want to go ahead and stand climb.
Well, I mean, I don't mean to belabor this Antarctic point, but John Morales from NBC6 in Miami. I mean, doesn't the subsurface melting that's going on in the Antarctic because of some warmer waters, the melting of that fresh water and refreezing of that water at the surface have to do with the expansion of the ice sheet around the continent?
Indeed, it does. But you know, as was said, you know, it's kind of a wash in terms of you know, how that's actually contributing to the overall global trend in sea level.
Thanks.
That is one of the reasons why we think that Antarctic sea ice is extending further than it used to, is because there's more fresh water being poured out there, and fresh water floats to the surface, as you pointed out.
Thanks, Jim.
Your level of information here is very good.
Yay!
Yeah, Craig Setzer, CBS Miami. And this question is kind of off field here,
Okay.
but since you touched on it yesterday, I'm going to ask you. And you used to work for the Climate Prediction Center.
Yes.
How do you address the NOAA seasonal hurricane outlooks being off, but not only being off the last 2 years, actually missing the sign of either being a below or above average season?
So the seasonal outlook relies heavily on the tools, which include the coupled models, and as was mentioned yesterday, all the models basically gave the wrong answer. So that means that we've got a long way to go in, you know, developing confident seasonal, you know, projections from the climate model. So that's one point. The other point I would make is when you go back and look at the verification of the seasonal outlooks, you will find that with the exception of this last year, that for several years, I think 5 years actually, the forecast did verify in a row. So I would argue there is skill there. Let me add another point just to reiterate something that was discussed yesterday, and that is that I think we have a lot of information beyond the seasonal outlooks that would be useful to the emergency management community based on improved understanding of the global climate system on subseasonal timescales. So for example, last year you may recall that there was a lot of warm air over the dry air over the Atlantic basin coming off of the African subcontinent that really shut down you know, the tropical cyclone activity. And I was very involved in the modeling community looking at that issue, and there was confident information on monthly timescales. So I would argue that it would have been very useful and productive to actually produce within the season updates of the seasonal outlook. In fact, they would have, I think, reflected what, you know, the signals that we were seeing. So I think the way forward is to produce more frequent updates of the seasonal outlooks, taking into account the improved understanding.
But the anomalous ridge and the dry air were in place in July, and then the August update came out still calling for an above or much above average season.
Again, because it's a seasonal outlook that I think doesn't properly reflect the within the season variability. So I think the anticipation was that there would be an uptick at the end of the season that would counter the sort of the shutdown basin in the July timeframe.
Wayne, Jim Cantori from the Weather Channel. This is regarding precipitable water values.
Yes.
Most recently, the event in Boulder. We're looking at, you know, out of season precipitable water values that are off the charts. So are you looking at events worldwide and seeing these values as well?
I'm really glad you asked that question, because if there's any bit of substance in my research portfolio any longer, it's actually looking at trends in precipitable water and how those relate to extreme rain events. So taking the Front Range flood event, one of the takeaways that I've seen is if you look at September, and you just look at daily precipitable water values along the Front Range, you will, first of all, there are not enough events in the historical record to develop any kind of a confident suggestion that there's an upward trend in precipitable water. That said, when you look at global values of precipitable water, there's no doubt. And I think that's particularly dominated by what's going on in the tropics. So the jury is, I think very much out on what that actually means in terms of, for example, if you think of teleconnections and influences on the jet stream, what that might mean, for example, storminess along the west coast, or in the summertime, what that might mean for wetter systems, that are stronger, in the Atlantic basin, tropical cyclone season. But with respect to the event, in the Front Range, we don't see any indication, at least in this part of the country, for trends in precipitable water that would explain the extreme rain event.
Looks like we have just one more question, and it's mine. This is Dave Jones with Storm Center Communications. Wayne, I was wondering if you could just make a comment about what kind of interest are you seeing from the emergency management or the state official's point of view with regard to climate information, and whether or not they're always turning to the Weather Service for information under the Weather Ready Nation as they build that up, but are they turning more for any climate information?
Dave, I thank you very much for that question, because I think that is the primary driver behind what I do. The demand for timely, transparent, and trusted climate information is just exponentiating. And again, I think the key thing is the pervasive nature of the weather-climate linkage. And my DNA, as I came out of the Weather Service, I spent 19 years doing climate in the Weather Service, learning, what the emergency management community is really doing on the weather side of the house and where we really needed to go on the climate side of the house. Bottom line is that I think that going forward, we have to, as a team, work together to, grapple with, the weather-climate linkage and what it is that we can confidently provide and sustain engagement between the public and private sectors in doing that. Listen to the emergency management community about what they can and can't use. So I would go back to needs assessments. And needs assessments are something that are really in their infancy in some areas, and I would put extremes in that category. So bottom line, Dave, is very much look forward to working to develop and deliver climate services that meet user needs.
That sounds great, Wayne. Thanks. Just a quick follow-up that hit me as you were talking. Is there an interest or a movement in the on the educational side? In other words, I know you want to educate the value of or the emergency managers and the value of climate information, but in the educational arena as well. Is there a push to increase the information flow that can be used in the classroom?
So that's a great question and segue to the Ned Gardner's a portion of the presentation here. And in particular, let me just emphasize that I come out of the modeling and prediction community, and what we really want to do is draw on our capabilities writ large for observing global observations, improving climate models that will allow us to predict and project the future climate state, and then work through our communication and education teams to get that information to the users that need it. And so I'm a believer, that communication and education activities that lead to a more climate literate public are the way forward.
One more question, Matt.
Yeah.
Hey, Wade, Matt Safino, KGW Portland. In regards to communication, I hear from my viewers, I hear from a lot of climate change deniers, and I imagine that many of my colleagues do as well. Oh, the models are terrible. We haven't seen any observed warning that can't be explained by natural causes. And then I think the biggest one is that it's a big scam, and it's just an effort on the research community to garner funding. All of those kinds of arguments that I'm sure you're familiar with. Can you give us a synopsis of how you respond to those types of comebacks?
Yes, so I don't know whether you're familiar with Ed Maybach's work on the different types of folks, ranging from the skeptics to the believers. Bottom line is, whenever I talk, and I actually talk a lot in public, I I always emphasize that I'm going to present the evidence to you. I can't necessarily influence, what you're going to take away. But if you think that the evidence is compelling, then I encourage you to act as you think is appropriate for your situation. So I don't get into the politics. I present the evidence, and I leave it up to you to make the decisions. And if that means writing your congressman, then so be it. But I don't want to stir the conversation, in the direction that, might mobilize, an inappropriate response. I present the evidence and leave it up to you to make the decision.
Wayne, thank you very much. If we could give Wayne a round of applause. Thank you so much, Wayne.
My pleasure.
This is terrific.